Okay, let's dive into this. You know, when we think about our homes, we rarely consider the silent, invisible war happening every single day. On one side, you've got human engineering, these complex, finely tuned machines meant to keep us perfectly comfortable. And on the other side, the relentless, absolutely unforgiving forces of the environment. So today, in this explainer, we're exploring the anatomy of an HVAC breakdown. We're looking at home maintenance not as some boring chore, but as an epic battle of survival. So, why do HVAC systems really fail? It's easy to look at a dead furnace and just think, well, it got old and finally gave out, right? But the data actually reveals a different, much more complex story. To find out why things actually break, we're going to look at Strongsville, Ohio as our fascinating primary case study. It's a place where specific, hidden regional forces push infrastructure to its absolute breaking point. Here is our roadmap for today. First, we'll look at the climate challenge. Then we'll dive into common system failures. After that, we'll break down the diagnostic process. And finally, we'll get into the actual economics of repair versus replacement. All right, Section 1, the climate challenge. Now, even if you don't live anywhere near Ohio, your own home is fighting its own local geographical battles. And understanding how your environment impacts your machinery is absolutely crucial. It's a secret to mastering your home's health. For Strongsville, it's a grueling three-front war. Because it sits directly in the Lake Erie snowbelt, it just gets pummeled by moisture-heavy weather. We're talking sub-20-degree winters that force furnaces to run in relentless, non-stop cycles just to maintain a baseline temperature. And then come summer, the air conditioners aren't just cooling the air, they're actually acting as massive dehumidifiers, working double time to literally wring that thick, heavy lake effect moisture right out of the house. The equipment is constantly under siege. But get this, the assault isn't just above ground. There's an equally destructive threat lurking right beneath the surface. The soil in this specific region has an incredibly high clay content, and over decades, this heavy clay acts almost like a giant sponge. It expands when it gets wet, it contracts when it dries out, and it causes the ground to gradually settle. That subtle but powerful soil movement, it's basically a slow-motion earthquake for the older home infrastructure hiding in your basements and crawl spaces. It relentlessly shifts and literally separates the mechanical systems that were designed to stay perfectly aligned. Moving right along to Section 2, common system failures. So, what actually snaps when a system is pushed to its absolute limit? Well, the casualties in this environmental war are highly specific. During a freezing cold snap, electronic igniters can crack from the thermal stress and constant moisture exposure. You'll literally hear the system trying to fire up, but absolutely no heat comes out. In the summer, that constant lake effect humidity we talked about causes severe moisture corrosion. That leads to tiny, undetected refrigerant leaks and ultimately total compressor seizure. And finally, older thermostats frequently fail. Why? Usually because of corroded mercury switches or just bad spatial placement on exterior walls, which feeds the system false data and forces it to overwork. But one of the absolute most insidious failures happens quietly, completely out of sight. Remember that shifting Ohio clay soil we just talked about? As it expands and settles, it physically tears ductwork joints apart, literally. Imagine the metal tubes carrying your precious conditioned air just separating at the seams over time. What happens is you end up with massive, hitting air leaks in your crawl space, forcefully blasting heated or cooled air directly into the dirt. Meanwhile, the living spaces inside your house stay freezing cold or sweltering hot. The system itself might be working perfectly, but the delivery mechanism has been completely destroyed by the earth itself. Okay, Section 3, the diagnostic process. Now, what's really interesting about this slide is how we pivot from the problem to the solution. Look, when a catastrophic system failure happens right in the peak of a demanding season, it's incredibly stressful. It's a full-blown emergency. So, to remove the panic and bring some order to the chaos, the industry relies on a strict three-step process, so you know exactly what to expect. Step 1 is contact and dispatch. This is where precise symptoms are gathered so technicians actually arrive equipped with the right replacement parts. Step 2 is diagnosis and approval. They use digital tools to identify the root cause, not just the symptom, and then give you a firm written estimate. And step 3 is repair and testing, where the fix is completed and the system runs through full environmental cycles. This ensures the exact same failure won't just pop up again the very next day. Now, if a replacement is on the table, the source highlights a completely critical industry standard called the Manual J load calculation. I know, it sounds super technical, but Manual J is really just a fancy term for ensuring your system isn't too big or too small for your house. Rather than just guessing the size based on a home's footprint, this methodology finds the absolute Goldilocks fit. If an air conditioning unit is oversized, it short cycles and completely fails to dehumidify the air. If it's undersized, it just runs constantly and burns out the motor. Manual J uses your home's unique layout, sun orientation, and insulation density to engineer the exact capacity needed. And operating right alongside that is Manual D. While Manual J dictates the size of the core machinery, Manual D is the strict science governing your ductwork sizing. Oversize your ducts, and you get massive velocity drops where air just awkwardly dumps out of the nearest vent, leaving rooms further away totally unconditioned. Undersize them, and you create high-velocity whistling that strains the blower motor. Manual D guarantees perfectly balanced, whisper-quiet airflow across every single room. Looking at this data really makes it tangible. You can see how square footage heavily dictates the required tonnage, or cooling capacity, of the unit. A 2,000 square foot home generally falls in the 2.5 to 3.5 ton range. But notice the variance there? A home might jump to the higher end of that required range if it has older, degraded insulation or maybe massive south-facing windows just baking in the afternoon sun. The structure's ability to retain temperature heavily influences the machinery required to regulate it. Section 4. Repair versus replacement economics. Let's get into the ultimate financial toolkit. This brings us to a universally stressful homeowner question. When do you stop repairing and start replacing? At what point does fixing an old, degrading machine just become throwing good money after bad? So the crucial point is this specific number right here, $5,000. It acts as a brilliant, incredibly easy-to-use mental model for home maintenance. It's the definitive threshold separating a smart, necessary fix from a total financial sinkhole. Let's walk through the math of the $5,000 rule. It's super simple. You just multiply the age of your system by the cost of the quoted repair. If the resulting number exceeds $5,000, a full replacement is mathematically the smarter financial move. For example, let's say you have a 12-year-old furnace and the tech hands you a repair bill for $500. 12 times 500 equals $6,000. Because that exceeds the $5,000 threshold, you are undeniably better off putting your capital toward a brand new, highly efficient system rather than patching up a dying one. But to effectively use that formula, you kind of have to map your equipment against industry lifespans. Around the 10-year mark, major mechanical components start to degrade, which triggers a general rule. If a repair costs 50% of a new system, replace it. By 15 to 18 years, air conditioners typically age out completely, just from exposure to the elements. And by 20 years, a furnace has reached the absolute end of its functional life. Efficiency plummets, and the safety risks really start to rise. When you're navigating a replacement, you'll hear about SEER, or Seasonal Energy Efficiency Ratio. This dictates the long-term economics. It's just the standard measure of electrical efficiency. Higher numbers mean significantly less wasted power and much lower operating costs. Local codes, like the ones in Ohio, now actually mandate a strict baseline of 14 SEER for any new central air installation, pushing the whole market toward greener, more capable technology. This brilliantly illustrates the real-world financial trade-off. A lower 13 SEER rating offers a cheaper upfront installation. That's ideal if you plan to sell the property shortly and just need functional equipment. But a 16 SEER system, despite the premium initial cost, it drastically slashes your monthly utility bills. Over a long-term hold, that upfront investment easily pays for itself during those heavy, humid summer months. Plus, it extends the lifespan of the equipment because it doesn't have to work nearly as hard. Okay, here is a highly actionable takeaway for you. If a replacement is inevitable, whatever you do not wait for the system to die in the brutal extremes of July or January. The data clearly shows the absolute best times to buy are the mild shoulder seasons, April, May, September, and October. By doing this, you completely avoid peak emergency demand, you secure better pricing, and surprisingly, contractors actually want to hear from you. They have the open flexibility to fit you into their schedule without rushing the installation. So we've seen how the environment relentlessly attacks infrastructure, how systemic failures cascade through a property, and the exact math required to fight back. The big question is your home's infrastructure prepared to survive the next season's battle? Take a look at your own system's age today and take proactive control over your mechanical health before the weather forces your hand. Thanks for joining me for this explainer, and keep learning.